Today we discuss chapter 7, geodesics. Before we going to give the definition of geodesic, we have another definitions, a vector field on a parameterized curve and a function on a parameterized curve. A vector field x along the parameterized curve alpha from I to Rn plus 1 is a function which assigns to each t belongs to I, is the domain of alpha, a vector x of t at alpha of t. Alpha of t is again a point in Rn plus 1. So that is x of t belongs to R alpha of t n plus 1. So this is the x of t is the is a vector at alpha of t for all t belongs to I. Now a function f along alpha is simply a function f from I to R. These are examples for a vector field and a function. If you consider a parameterized curve alpha is from I to Rn plus 1, then the velocity vectors give an example of a vector field along a parameterized curve alpha. This this alpha dot defines a vector field along alpha, and norm of alpha dot that gives its length that defines a function along alpha. This is an example. This is an example of a parameterized curve and a vector field defined on a parameterized curve alpha dot t. And if you consider the length of this alpha dot at each point t belongs to I, you can get a function along this alpha t. But the idea is when you consider this point, at this point you can get for different values of t, you can get say t1 and t2, you can get alpha of t1 equal to alpha of t2. But the vectors assigned at these 2 points are different and really different. So this is alpha dot of t1 and alpha dot of t2. So this example gives the idea that the velocity vector field along a parameterized curve of alpha, and these are alpha of t1 and alpha of t2, but the vector assigned at these 2 points are entirely different. Okay, now we are considering vector fields and functions along parameterized curves as restrictions. Thus, if x is a vector field on U, or U is an open subset of Rn plus 1 containing image alpha, then X composition alpha is the vector field along alpha. Similarly, F composition alpha is a function along alpha whenever F is from U to R, but this U contains the image alpha. So this is the idea. So this is the form of a vector field along alpha. X of t is equal to alpha of t. At the point alpha of t, assign a point in Rn plus 1. That is denoted as x1 of t plus x1 of t comma etc xn plus 1 of t. So this each xi is a function from I to R. Okay, this is the idea. So that means each xi is a real valued function defined on an interval. Okay. So if this each xi is smooth, that is differentiable, then you can say that this the vector field along alpha is differentiable. So the derivative of the smooth vector field x along alpha is the vector field x dot. This is denoted by x dot along alpha. This is the derivative of a vector field along a particular parameterized curve. This is the idea. This is not the derivative of the whole x. This is not the total derivative of x. This is the derivative of x along a particular curve, along a parameterized curve. So that is defined as x dot t is equal to alpha of t and derivative of each of its components. So x dot t measures the rate of change of the vector part x1, x2, etc. xn plus 1 of x of t along alpha. So thus, for example, the acceleration alpha double dot of parameterized curve alpha is the vector field along alpha obtained by differentiating the velocity vector field alpha dot. Okay, so once you consider this is the velocity vector field along alpha, then you consider the derivative of this vector field. So derivative is defined as alpha double dot, or you can write it as alpha dot dot, and it is denoted by limit t tends to t naught uh, alpha dot t minus alpha dot t naught divided by t minus t naught. This is the definition. So this will, if you take, this is t, this is alpha dot t, and this is alpha dot t naught. You can consider the difference between these two. When you translate that vector to this one, this side, and consider the difference alpha, this is alpha dot of t1, then this will give the alpha dot t1, alpha dot t minus alpha dot t naught. Similarly, at each of these consecutive points, you consider the difference. Okay, so when t by letting t tends to t naught, you can get a vector which pointed towards the towards this side as a velocity acceleration vector. So this is one of the examples. When you consider the two consecutive derivatives here, alpha dot here, and consider the difference between these two. Okay, so that will give the alpha dot. When you translate this to this point, so that will give the alpha double dot t naught. So this is what we call acceleration vector. When we consider any vector, any parameters in the curve like this, when you consider two distinct point, then the difference pointed towards like this. So when this close to this point, you can get the velocity derivative velocity vector, that is acceleration vector, pointed inside this this parameterized curve. These are the rules for the derivative of a vector field along alpha. Alpha is from I to Rn plus 1. Then x plus y is equal to x dot plus y dot. So this is the this is x plus y whole dot. So this is the derivative of x dot plus y dot. And if you consider a scalar function f, then fx dot, okay, that is the derivative of this one, that is f dash, this is the derivative of this function, x plus f times x dot, this is the derivative of x along alpha. Then x dot y derivative, this is a scalar function, that's why we use this symbol. So this is d by dt of that scalar function. So that is that can be written in terms of the derivative of a vector field along alpha. So that is x dot dot y. This is the derivative of a vector field along alpha plus x dot y dot. This is again a derivative of y along the vector field y along a parameterized curve. So we can say that whenever x, y are two smooth differentiable vector field, then its sum and scalar multiple and dot product are all are differentiable and follow these rules. Now we will define geodesic. Geodesic in an n surface, S subset of Rn plus 1. So this is an n surface. Then what is the requirement? This can be written as f inverse of some c, and this del f of p not equal to 0 for all p belongs to S. This is the requirement. And geodesic is a parameterized curve on this S. Say alpha from I to S, whose acceleration is everywhere orthogonal to S. That means when you consider the acceleration alpha dot, this alpha dot is always belongs to alpha derivative of alpha dot, that is alpha double dot or alpha dot dot, is always orthogonal to the tangent vector. Okay, so that is when you consider alpha double dot of t, then that belongs to the perpendicular of the tangent space. Okay, so this is what we call the geodesic. Thus, geodesic is a curve in S which always goes straight ahead in the surface. Its acceleration serves only to keep it in the surface. It has no component of acceleration tangent to the surface. That means when you consider any vector, then that can be decomposed into two parts, or it can be written as a combination of tangent space and the normal space. A vector that is, if this is tangent space, a tangent vector in the tangent space, and this is a vector in the normal space. Any vector can be decomposed into this form. Then we can say that if in the case of acceleration, In the case of geodesic, there is no component in the direction of the tangent space. That is only in the direction of any vector. If you choose any vector, you can say that that is in the acceleration is in the direction of a normal vector, okay, not in the tangent vector. Note that geodesic have constant speed because we know that alpha dot t belongs to S alpha of t. That means if you take any vector in the tangent space, this alpha alpha double dot. If you consider any alpha t, then alpha double dot belongs to this alpha S alpha t perpendicular, and alpha dot is always a tangent vector, so that belongs to this. So you can say that product dot product of this and this will be 0. So the consequences alpha dot t dot alpha double dot t is always 0, because since alpha is geodesic, we can say that this is in the direction of the normal, or it is in perpendicular to the tangent space, and this is the vector in the tangent space. Then what is d by dt of this norm alpha square? So that alpha dot square, that is d by dt of norm alpha dot square can be written as alpha dot alpha dot. By taking the derivative, you can get alpha dot alpha double dot plus the same thing. So that is 2 times this, that is equal to 0. So this shows that a geodesic have the same constant speed. The converse of this theorem is also true, that is included in the exercise. You can prove that there is a parameterized curve alpha and whose derivative, that means whose length, whose speed is constant, then you can get that alpha as a geodesic. These are some of the examples. If an end surface S contains a straight line, line segment alpha of t is equal to this, then the segment is a geodesic. Indeed, alpha double dot is always 0. That's the reason. So you can say that this is in the this is perpendicular to this tangent space. So this is obviously these are the all straight lines are the geodesics. For each a comma b comma c comma d belongs to R, the parameterized curve alpha of t defined by this manner is a geodesic in the cylinder x1 square plus x2 square is equal to 1 in R3, because this alpha, this acceleration vector is this one. Okay, you can easily prove that this is in the direction of the n of alpha of t, that is in the direction of the normal, which is perpendicular to the tangent space. So you can say that this is also a geodesic. This is an example of geodesic. There is one more example. You can easily verify that this is also geodesic. In the next part of this chapter, we will discuss the existence of a geodesic. Once you are given a surface, then you can easily prove that there exists at least one geodesic passing through a point P on the surface, and if you choose a particular direction. If this is the case, if you choose a point on the surface and define a velocity vector or a vector in the tangent space, you can get a geodesic which passes through, there exists at least one, or the maximal geodesic which passes through this point. So that is the next part of this chapter. We will discuss that in the next class.